Today we'll be looking at how this new machine splits moon dust into oxygen and metal. If you're new to this channel, welcome. This is Mr. Singularity, where we explore the illuminating scientific and technological breakthroughs shaping the future as we know it. Like the old pioneers, space travelers are going to have to survive off of the ground. But if self-sufficiency on Earth is difficult, orders of magnitude are more daunting in space, where there are no trees to create shelter, no plants and animals to feed, no water to drink, and no breathable air. Prospective space explorers will have to use a heavy dose of science and resourcefulness to withstand dangerous worlds on the Moon and Mars. Luckily, they're going to have ties to some of the best minds on the planet. Any of these minds, now employed at the European Space Agency, are making a computer that turns moon dust into oxygen to breathe and fuel rockets, and metal for construction. Moon dust is nearly half oxygen. Indeed, the atmosphere of the moon is a desolate landscape. It's like being exposed to the vacuum of outer space, with the modest bonus of a little ground beneath your feet and dust on your boots. It is this fine, gray, and bone-dry dust that will provide to be an invaluable resource for lunar homesteaders. Identified as lunar regolith, the soil of the moon is 40 to 45% oxygen by weight. Bound up in mineral and glass oxides, oxygen is the most common element on the surface of the Earth. Oxygen is also evidently essential for breathing oxygen, and it's the main component in rocket fuel. But you can't breathe or fuel ships with moon dust. This is where the ESA comes in. Alchemy of lunar success. The ESA team, headed by University of Glasgow Ph.D. candidate and ESA researcher Beth Lomax, is applying the industrial approach developed by the UK company Metallysis. Named molten salt heat electrolysis, the procedure requires heating up a basket of artificial moon dust, which is a near resemblance to the actual thing, and calcium chloride salt at 950 degrees Celsius. The researchers then broke the oxygen with an electrical current, leaving behind a pile of metal alloys. The method will isolate 95% of the oxygen in 50 hours, but 75% can be removed in only the first 15 hours. Last October, the team released a proof of concept, which they claimed was a major improvement on other related processes that contain less oxygen or need even higher temperatures. And there is room for change. To that end, the team revealed last week that they were setting up a new oxygen plant in the Netherlands to further optimize things. The main aim is to reduce the temperature. The higher your temperature, the more energy you require, and electricity is going to be a finite resource on the moon. The team has no goal temperature in mind, but they know they can do better. How much better depends on how low temperatures impact other facets of the process, like efficiency. Ice and moon dust. In addition to oxygen bound up in lunar soil, we know that the moon has water. Although the specifics are still somewhat veiled in mystery, scientists agree that the water of the moon takes the form of ice in the permanently shadowed regions of the poles. We're going to need water to drink, of course, but we can also split it into its elemental elements, hydrogen and oxygen, by electrolysis. As long as we can get to the moon's ice, how do the energy needs of the ESA process stack up with the electrolysis of water? The two resources will definitely have separate trade-offs to remember, though we may well need both to support a sustainable presence on the moon. Since the ESA process requires high temperatures, it is very energy-consuming relative to the water electrolysis that can be conducted at room temperature. Yet the dust of the moon coats the entire planet as far as the eye can see. Grab a shovel and fill up a bag. On the other hand, the moon's ice will be rarer and even more complicated for me, and we're not aware of its structure or what kind of refinement it will take to make it available. There is still something else to consider, that pile of metal left behind after the oxygen has been removed and siphoned away. This metal may prove to be a durable building material, something that the ESA team will also be looking into in the coming years. Can metals be printed directly in 3D, for example, or will they need refining, the Meurisse asked. The precise combination of metals will depend on where the regolith is acquired from the moon. There would be significant regional differences. Then the team will develop a pilot plant that could run on the moon, but will not be sent there by the mid-2020s. In the longer term, if the technology becomes versatile and spaceworthy, it might help to make the moon a gas station for spacecraft in Earth orbit and beyond. Manufacturing fuel on the lunar surface can prove more cost-effective than dragging it from the Earth. At the end of the day, astronauts will use moon dust to breathe, construct, and fuel missions throughout the solar system. What's your take on this? Let me know down in the comments below and check out one of these other videos. This has been Mr. Singularity, and I'll see you on the next one.